Okay, guys, now comes the very last section, section 4.2, and I want you to know that I'm going to take a very simplistic and practical point of view, and that is section 4.2 is a theoretical construction whose real application is not in the world of theory. And so we're going to only look at a couple of very basic ideas associated with it. First off, there is a definition which is important in this area, and that is our definition of the covariance of x and y. The expectation of the x minus mu of x times the y minus the mu of y. Now, the linearity of this operator says that after multiplying this out, that we can just do the pieces parts. But mu and the expectation of y is just mu of x, mu of y. Mu of y times the expectation of x is mu of y, mu of x, mu of x, of y. And you see that we have several redundancies here. And the covariance is the expectation of xy minus mu of x, mu of y. Which is very nice, because if you just happen to set x equal to y, then the covariance of xx becomes the variance of x, which is very nice. The formula is consistent. In addition, it even looks like the variance formula, expectation of x squared times mu of x squared. Now, there's a second thing that's important in this section, is that we make a definition of a new concept. We're going to define the variable rho, and that's the Greek r, to be the covariance of xy over sigma x, sigma y, which, by the way, we also use this notation for the covariance. So here is a number that we're simply going to define, and it is called the correlation coefficient. Now, why we defined it, we're going to discover very quickly here, and it's quite simplistic in its implementation. The theory side is not quite so terribly relevant. In fact, I welcome you to read the example 421 so you can see these things calculated, but in general, that's not really what I'm interested in. But first off, let's just take a picture of a theoretical joint probability density function. So this is a joint PMF. Now, what happens if we would just like to find a line that goes through this data that represents that theoretical points, kind of a summary of the PMF? Well, one thing that we could say is let's just force it to go through a special point, force this line through mu of x, mu of y. So if this line is going to represent a summary of the data, then it's very reasonable that it go through this. And we will see that that assumption is kind of irrelevant. But under that assumption, we would like to find a line y minus mu of y, which will be some slope b times x minus mu of x. That's the point slope form of a line. Why statisticians use b here totally befuddles me. However, I recommend that you take a look at TI 83s, 84s, 85s, and notice that one of the linear forms of a line that are used in the stats is y equals a plus bx. How's that for a strange use of a and b? The statisticians were the people that developed this. Now, if we want to find the best one, well, we'd like to make sure that these distances here are minimized. Well, instead of minimizing the distances, let's actually define a function, k as a function of b, which is the expectation of y minus the mu of y. I'm going to subtract off the b times x minus mu of x. But we'd like these suckers squared. Now, what this expectation does is it weights every point by its probability, and it squares these distances. I'm not going to address why we're going to do the square right now, but it would be nice if we could just find the best line that minimizes this. Well, that means we'd like to know what this expectation is. Well, that expectation is fairly straightforward to calculate it. Square this out, put all the terms together, and lo and behold, it's fairly simple. It's sigma of y squared minus 2b, and there's a covariance in there, and if we put in a row, we'll have a sigma x, sigma y, plus b squared, sigma x squared. That's through algebraic simplification and the definition of every symbol. So what's interesting here is that the line we're trying to fit to our theoretical data has a very simple expression, constant, 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 constant. It's just a quadratic. You take the derivative of this quadratic, why we get minus 2, ooh, is that, b goes away in the derivative side, minus 2 rho sigma x sigma y plus 2b sigma x squared. And if we choose to set this equal to 0, well, turns out that b then has to be, well, move everything to the other side and solve for b, and we get b equals rho times sigma y over sigma x. So, what do we have? Well, we have a joint PMF. We have a known point mu of x, mu of y, and now we have a slope, which is this number rho, which we can calculate from the P of f, sigma y over sigma x, and we have discovered that the, quote, the minimization of the squares of the distances from this line produce the line y minus mu of y equals rho sigma y over sigma x, x minus mu of x. So this is often referred to as the least squares calculation. Well, let's ask ourselves, does this make sense? What happens if our PMF was actually a straight line, if the variable y was actually some mx plus b? Would have that been the case? And the answer is absolutely. Just take a look at the definition of rho again. Back a couple of pages there, definition of rho. Got to make sure I write the right one down. Rho is the covariance of x, y over sigma x, sigma y. But when they're linearly related, then the covariance carries the slope through just as well as the sigma y carries it through, and lo and behold, we get a 1 out of the deal here, or a minus 1 depending if the slope was positive or negative. So we get a plus or minus 1 in this row. And you know what happens? This equation is exactly calculated by that equation. They're the same. So if the joint probability density function was a linear relationship between y and x, lo and behold, this line is exactly the line we expect. Now, it turns out there's an exercise in the book. You don't have to do this, but take a look and read it. If we, let me get the number, I think it's 4.2-5. Instead of forcing it to go through mu of x, mu of y, if you assume a y equals mx plus b going through the joint PMF, as you work your way through it, you would discover that this passes through mu of x, mu of y, under the same assumption of minimizing the expectation of the squares of the distances. And once it passes through, we've just done the calculation that says this is the equation you must get. So it doesn't matter if you're minimizing the squares of the distance from a given line or minimizing the squares of the distance from this particular line, it produces the same answer. Well, now we can calculate one of these, which is very boring. actually has hardly any good meaning, except when we're going to take a look at the binormal distribution. It really doesn't have much use. What I'd like to do is I'd like to mention some basic facts that we know about this thing called the regression line. First off, I'm going to calculate what the value is for the minimization of the k of b. So our k of b, which was sigma y squared minus 2b rho sigma x sigma y plus b squared sigma x, if we actually plug in, set b equal to this value rho sigma y over sigma x, and we do some pretty straightforward calculation, it simplifies to the following fact. Sigma y squared 1 minus rho squared. Now, one might ask, why did we evaluate it? Well, the answer is we gain a wonderful little piece of information. K of b was the expectation of a square. So that means this has to be greater than or equal to 0. But since this is already squared, this forces 1 minus rho squared to be positive, which forces rho to be located between 1 and minus 1. So this thing called the correlation coefficient doesn't take on very many values. It only takes on values between minus 1 and 1. Now, I'd like you to notice that the 1 and minus 1 we discussed already. If we set a joint PMF that actually works under this relationship, this causes a 1 or a minus 1, depending if it was going downhill or uphill. So in some sense, the value of 1 and minus 1 is talking about the possible linearity of the relationship between y and x. It doesn't have to be a linear relationship, it's just a description of the PMF. But in a moment, we'll discuss why that's so powerful. But here's the next thing. What happens if rho up here is not known to be 1 or minus 1 because of this? What happens if rho is just known to be approximately or very, very close to 1 or minus 1? Well, then this expression right here is basically 0. And so the expectation of the minimization says that this is very, very small. This means that in some sense it's very clear that rho measures approximate linearity when rho is near 1 or minus 1, very linear joint PMF, and if rho is approximately 0, well, very nonlinear. Because a set of lines that it could be just as much above and below it, not talking very much about anything. Well, now comes the real important part of this discussion. That was theory. What happens if we're doing application? So here comes the biggest use of section 4.2, and this is the future use of it. Let's suppose for some reason you believe that y is approximately mx plus v for two variables that you really don't know much about, actually. If you don't know much about x, you just assume y is related to it. For example, here might be the weights and heights of children in their first year of life. It would be very reasonable to expect that the distribution of weights might be unknown to you, but once you know the weights, you expect the h's to respond. So maybe there's many more dots here and very few here that the weights of children converge. I have no idea the distribution of X, but the Y, the height, seems to respond to it in a linear fashion. If you believe that, well then this data that one has gathered, data, empirical, not theory. Well, if we just assume that it's theory and then ask for the regression line that goes through it, well, that means it's very reasonable that we use that covariance and we use the value of rho, but we use it on the empirical data, the descriptive data, and we set rho equal to the covariance of the xi's comma yi's over the standard deviation of x and the standard deviation of y's, the empirical ones, not a theoretical one. And we discover that we have this y minus the, now mu of x is the theoretical average. When you have some data, we call it x bar. So then we'll have a b. Oops, that was supposed to be a y bar, and this will be an x minus x bar. This equation, which uses the b equal to rho times s sub y over s sub x, seems like a theoretical application and a very reasonable approximation that theory, if you believe this, then whatever the distribution for x, then you would expect this equation to represent it. And that's called the regression line used on empirical data. And it's very powerful because we have reasons to believe that height is related to weight without knowing the distribution of the weight amongst the children. We just have that linear relationship. All right, now there's one more thing in the section that's kind of interesting. And those of you that read the book, I think you should chew this one over. It is example 4.2-3. 4.2-3 makes this very simple statement, and that is, it says, because the support of the joint PMF, which they didn't put that in, the support is not rectangular, and they put quotes around that. They say x and y must be dependent. That means it's just the picture of a PMF is enough to tell you that it can't be a independent set. That somehow independent sets have to look like this. This needs to be the support of an independent, and this automatically means it's dependent. That doesn't mean it is independent, but this definitely means that it's not independent. That's an interesting thing to mull over, and I think some of you that are more theoretically minded should take a look at it and see if you can prove that. I'm not going to ask it on a test. It's just one of those sneaky comments that authors have put in a book that should maybe put a little light go off in your head. Was it proved earlier? Is it something that you know? It is a picture. And the picture here is a piece of theory. Now, what do I expect you to know out of all of this? Well, in the theory world, it's very little relevations. We use it in the empirical world. I want you to know the definition of covariance. I want you to be able to calculate a rho. And I want you to be able to say that rho is a measure of linearity, and if rho is +1 or -1, it's an absolute linear relationship within the joint PMF. That is the entirety of what I want you to get out of this section. The theory part has very little future applicability for us, except for a small piece.